Okay, we're back now, and as I said a moment ago, what we're talking about here is using the concept of significant figures in order to avoid overstating the accuracy with which we know the results of calculations. The number of significant figures in the answer to any given calculation is going to be limited by the number of significant figures in the least accurately known number that goes into the calculation, because that's really what limits the accuracy with which you can possibly know the result. Before we can actually get into that, how to go about that, though, we first have to get into the idea of how do you recognize significant figures? You know, how, just given a number in a measurement that you didn't do yourself, how do you recognize which digits in the number are significant and which ones aren't? So that way you can recognize which number going into your calculation has the fewest significant figures in it. And so determining the number of significant figures is a pretty important thing to be able to do. So for now, we'll work on determining the number of significant figures just in a number, and then we'll go on to see what you can do with those numbers to determine the significant figures in the answer to a calculation that you do with those numbers. Well, in determining the number of significant figures in a number, the first rule is actually very simple. And that is that non-zero digits are always significant. That's a very simple, straightforward answer. As you're looking at the digits in a number and you're counting along, if it's not a zero, it is significant. It's the zeros that are the problem. Okay, for the zeros, well, it turns out there are different kinds of zeros. The zeros at the beginning or the left-hand side of a number are not significant. And that's because the zeros at the beginning or the left-hand side of a number are normally just there to locate the decimal point. They don't actually mean anything in terms of the measurement. In the middle of a number, in other words, between numbers that are not zeros, those are significant. Okay, now the fun part. Okay, so we've got at the beginning of a number, zeros are not significant. Easy. In the middle of a number, that is between other numbers that are not zeros, they are significant. Now comes the real fun part. At the end of a number, they may or may not be significant. They are significant if there's a decimal point, and only if. And that decimal point doesn't have to be in with the zeros at the end of the number. that decimal point could be anywhere within the number. And so if there's no decimal point, then the zeros at the end are not significant. So those essentially are the rules. The rules in the book are stated a little bit differently from this. I think actually laying it out this way is simpler and more straightforward than the way the book presents it. But by all means, look at what the book says, and if that makes more sense to you, then learn it that way, because either way, the result is the same. So to summarize what I said here, zeros at the beginning of a number, not significant. In the middle of a number, significant. At the end of a number, significant if there's a decimal point, otherwise not significant. And so to try some, and before I go on to examples, some numbers actually have infinite significant figures. That is, they're known with infinite accuracies. And things like that would include integers, numbers from counting objects. Like if you say you've got 3 pencils on the desk, that would be considered exactly 3.000 on to infinity. If you could say you got a dozen donuts, that's 12.0000 on to infinity. So integers, counting numbers, definitions. And also conversion factors within the English or metric systems. It's important to remember, though, that conversion factors between English and metric systems are rounded off, and those are not exact numbers. But within the English system and within the metric system, conversion factors are infinite, infinitely known. For example, when we say 1 foot is equal to 12 inches, that 12 would be considered exactly 12 inches, no more, no less. Or for instance, 1 meter is equal to 100 centimeters. That 100 is considered to be an exact number with infinite significant figures. Okay. So those are the essential rules for significant figures. in the case of deciding how many significant figures there are in a number, we can try a few examples. You might actually, it wouldn't be a bad idea to maybe pause the video after I write the number and see if you can guess the number of significant figures before I say the answer. If you have, say, a number like 85.3, that's pretty straightforward because there are no zeros in it. So that's obviously 3 significant figures. 1, 2, 3. If you have a number though like 0.03, how about that? Well, that is only 1 significant figure because again, zeros at the beginning don't count. And both of these zeros are at the beginning. About 303. That's actually 3 significant figures because the 0 between the numbers that are not zeros, that counts. How about 30,003? Well, actually, that has 1, 2, 3, 4, 5, because all of those zeros in the middle of the number count. I wanted to include that example because sometimes when it sounds like when you say zeros between non-zero digits count as significant, it kind of sounds like it has, each zero has to have a non-digit zero immediately on either side of it. And that's not the case. As long as there's non-zero digits anywhere on the left and the right, that zero will count. So even this 0 in the middle that's between 2 other zeros, it still has a 3 to the left of it and a 3 to the right. So that counts as significant. All of them do. 5 significant figures. Now, how about 0.03030? I had a thing for 3s when I wrote this up for some reason. In this case, that has 4 significant figures. The zeros at the beginning do not count. The 3 obviously counts. The 0 that's between non-zero digits counts. The other 3 counts, obviously. And the 0 at the end counts because there is a decimal point way up at the front. Like I said, it doesn't matter where the decimal point is in the number. If there's a decimal point anywhere in the number, the zeros at the end count. We have maybe 303.0. That would be 4 significant figures. All of them count in this case. The 0 in the middle counts, and the 0 at the end counts again because there is a decimal point. For 3030. There is some ambiguity in numbers like this. Strictly speaking, you would say there are 3 significant figures, the 3, the 0 that's between the 3's, and the other 3. But it's ambiguous. It's because of the way we write numbers in the Arabic numeral system. It's possible that you could get stuck having to write, or basically, it's possible that you can write a 4-digit number like this, and it would appear that that last 0 doesn't count because you didn't put a decimal point in it. This is, in fact, the common way to do things, and it's not strictly correct, but people sometimes do it. Even in science, sometimes we forget. So when faced with an ambiguous situation like this, we usually go with the smaller number of significant figures. So the more correct answer here would be 3 significant figures. The 0 at the end strictly speaking, would not count because there's no decimal point in the number. If you want to convey a number like this with 4 significant figures and you want to make sure you're not misunderstood, all you have to do is put a decimal point at the end of it. Now there's no doubt about it, that is 4 significant figures. 1, 2, 3, 4. Okay, so those are some examples. The reason that determining the number of the number of significant figures in a number is important is because we will then often use those numbers in calculations, and we want to know how many significant figures we should be including in the answer to the calculation. So how do you figure scientific, I keep wanting to say scientific notation, getting ahead of myself. Significant figures when you're doing calculations, it actually differs for multiplication and division versus addition and subtraction. So for multiplication and division, in multiplication and division, the answer should have the same number of significant figures as the least accurately known quantity that went into the calculation. Okay, the least accurately known number that went into the calculation. Okay, so for an example of that, let's see. Say if you've got a turtle and it walks 21.4 centimeters over 8.5 seconds, the velocity of the turtle would be distance over time, or 21.4 centimeters divided by 8.5 seconds. And if you put that into your calculator, the calculator will give you 2.517647059 centimeters per second. And as you can probably intuitively guess, that number is kind of ridiculously long. Even if you know absolutely nothing about significant figures, you're probably going to want to cut that number off at some point and not use all of it, just because that it really is ridiculously long. And it's ridiculously long because the calculator doesn't know about significant figures. The calculator assumes that every number that you entered has zeros after it. So it assumes that 21.4 is 21.40000 on to infinity. And it assumes 8.5 is actually 8.50000 on to infinity. And it divides those numbers and it gives you this huge thing. So what we have to do when we're doing calculations is sort of correct for the calculator. We sort of have to keep an eye on the calculator and make sure that that it doesn't overstate things. Okay, so if we look at the numbers that go into this calculation, 21.4 has 3 significant figures. 8.5 has 2 significant figures. So the answer should have 2 significant figures. We knew the time less accurately than we knew the distance. And so the time is going to limit the accuracy with which we can know the velocity. So rounding this number off, to 2 significant figures means the 2 counts and the 5 counts, but everything after that has to go. When you round off a number for significant figures, you look at the first number that you're going to drop. In this case, it's a 1. If that number, the first number that you're going to drop is 4 or less, then the numbers you're keeping can stay the same. If the first number you're dropping is 5 or greater, the custom is to increase the last digit you're keeping by 1. So basically to round it up. But again, since it's a 1, we just leave it as 2.5. And that is the correct answer to the correct number of significant figures for that question. Okay. And so that's how you can round off for significant figures. Let me see here. Okay, another example might be, for example, if the turtle walks 12.27 seconds at a constant 2.51 centimeters per second. What distance is covered? Well, distance is velocity times time. And actually, even if you don't know this, one advantage to keeping an eye on the units is that you can often do a calculation and come up with the correct answer, even if you have no idea what the question is talking about, if you look at the units for the data given and make sure that they come out to the correct units that you want. In this case, we're asking for a distance, which would be a unit like meters, or maybe in this case, centimeters. And we're given centimeters per second and seconds. So how would you get centimeters out of that? Well, if you multiply them together, seconds will cancel and you get centimeters. And indeed, that is what you're supposed to do. So let me see, 2.51 centimeters per second times 12.27 seconds. Notice that seconds cancels and centimeters becomes the unit for the answer. And let's see, the number that the calculator is going to give you is 30.7977. Is that actually what it gives you? Yeah, that's the whole answer that the calculator gives you. 30.7977, that's pretty long. It's a pretty good bet. That's too many significant figures. And sure enough, when you look at the numbers over here, it is. 2.51 is only 3 significant figures. And 12.27 is 4 significant figures. So we have to cut this number down to 4 significant figures, or sorry, 3. that means the 3 can stay, the 0 can stay, and the 7 can stay. But the first number we're dropping is a 9, which means the last number we're keeping should go up by 1. So the proper number of significant figures, that would be 30.8 centimeters. Okay. Maybe another one. How much time would it take for the turtle to walk 17 centimeters at that same rate of speed? Well, let's see. Time is equal to distance divided by velocity, or distance times 1 over velocity. And you can actually see how the units work out if you actually do it this way, because distance is 17 centimeters, and velocity upside down, well, it takes, or rather the turtle travels 2.51 centimeters in each second. The reciprocal of that means that it takes 1 second for every 2.51 centimeters. Now you can see clearly centimeters cancel and you end up with seconds as the answer, the unit for the answer. And your calculator will give you this number, 6.772908,367. Too many significant figures, obviously. 17 is only 2. And 2.51 is only 3. So 2 significant figures is what we need for the answer. And if we look at the number we've got, we see it's 6.77 blah, blah, blah. That means if we need 2 significant figures, that means the 6 can stay and the first of the 7s can stay, but everything else has to go. The first number we're dropping is a 7, which means the digit before it has to go up by 1. So this becomes 6.8 seconds. All right. Yeah, so that's just some simple examples for multiplication. Oh, what is the matter with me today? Multiplication and division. The rules for addition and subtraction are different, but they sort of follow the same concept of going with the least accurately known number that goes into the calculation when you're deciding how many digits should be in the answer. Okay, having said that, I see that we're a little over time now, actually, so I'm going to stop there and continue with the third segment in a moment.